3-2, day 1. First day we're covering logarithms. Couple general pieces before we dive in. Stay focused the whole time that logarithms are the inverse of an exponent. Okay? You'll see a lot of ways they're like the opposite. Kind of like multiplication and division, addition and subtraction, the operation of squaring and taking a square root. It's very much like that. Okay? A lot of times as you're studying logarithms, you can get kind of stuck on, you know, what are they and what do they do? They can feel kind of abstract. Stay on that concept. They are the opposite of an exponent. Okay? From there, all we're going to do with them today is just make some graphs and evaluate them. Okay? There you see on this slide, that's log base 2. We'll make that graph in just a little bit. All right, let's define a logarithmic expression. I'm really going to write it in terms of like a function. And there are a lot of times that we think about logarithms as functions, which again, that's just a way of saying that, you know, you put in a number for x, you get one number out as an answer for y. If an expression does that, it's a function. Okay? There's base A. A couple rules about A. It does need to be positive, and we have to be specific to mention that it shouldn't be 1. It's the same deal. If you're ever making a base 1 on an exponential or a logarithmic function, it becomes linear, and it really doesn't model the rates of change between those two variables the way you want. Right here, x. You'll see this come up a little bit too. Needs to be greater than 0. Negative numbers there don't work. It's got they have a restricted domain. Now, as far as kind of how they're evaluated, and we're going to get to that in the next slide here. This goes right along with that. Notice how like the x and the y variables switched. An exponential equation that has the variable switched is the inverse, and those expressions are equivalent. Okay, solutions to one are going to be solutions to the other, and this can be really helpful when you're evaluating. Let's drop down here and do that. Okay. For example, in our first one, let's call it example A. We have y equals log base 2 of 32. Okay, and I'm treating 32 like an x value, that I'm putting that in. You know, what am I going to get out as a y value? That expression can be really hard to kind of visualize what's going on. Okay, if you're going to evaluate without any assistance from a calculator, it's, I think, a good idea to switch it up and to say, okay, you know, the base is 2, but this, that's really what that expression is asking us. What power would we have to raise 2 to get 32? 2 to what power is 32? Okay? That, as far as kind of finding a solution to it, is a lot easier to visualize and a lot easier to check, you know, guess and check a few options, because I don't think it would be all that long before you'd see that it's 5. Okay? So now over here with this expression that was log base 2, it means we put in an x value of 32. We got a y value of 5. I'm going to throw some problems with some different bases at you here, but the idea is going to be the same. Okay, the base is now 3, right? And for an x value, we've plugged in 1. What do we get for a y value? I would immediately head over here and say, okay, base 3, 3 to what power is 1? Okay? Again, that's asking us the same question. Okay? The y value for the exponential expression on the right is going to be the same value as the logarithmic one that's on the left. Turns out it's 0. 3 to the 0 power is 1. Log base 4 of 2, which is asking us 4 to what power is 2. Again, you might be left with a little bit of guessing and checking going on there. This one's a little bit tougher to do. If I'm going to have you evaluate them by hand, okay, evaluate them by hand, the numbers aren't going to be super terrible. And if you're guessing and checking, you're going to get to kind of a nice answer relatively quickly. If the numbers get really nasty, and we'll see this happen, we'd have to go to a calculator at some point in time. Okay, that's going to be a part of dealing with logarithms. Is for a good chunk of them, we'll need assistance from a calculator. And here's one more. Check out this one. No base is written at all. What is that about? You could see that happen, certainly. If you do have a logarithm without a base, remember it's 10. Okay? 10 to what power is 1 over 100? And it's negative 2. Okay? That might be another one. You have a couple cases to check, but I think relatively quickly, you'd probably find that 10 to the negative second power would get you 1 over 100. All right, a few basic properties of logarithms that I want to talk about a little bit. These are kind of based on the same concepts as the previous slide, so maybe a better thing to call them versus properties would be shortcuts. It's kind of what they are. And notice all these are just base A, so these are some properties here that are being generalized that they work for any base. Okay, as long as it's positive, as long as it's not 1, which we talked about in the first slide. A to what power is 1? We saw that one come up on the other slide, that it's 0. Okay, so if you're taking log base anything of 1, that expression equals 0. Every single time the base doesn't matter. What if you have something like this in property number 2, where the base and what you're taking the log of are the same? The base and what you're taking the log of are the same. That expression is always 1. Here what we see is this one won't come up a lot in the next few days in class. When we get to solving in section 4 and 5, this one's going to come up quite a bit. What you really have is a log expression, base A, with an exponential expression of the same base inside. Okay? Remember what I said right away. Logs and exponents are like inverses. Okay? When you're using them in the same expression, they cancel each other out, and that would just equal x. Okay? Again, property number 4 won't come up right away. Later in the chapter it will. But if you do have like 1 log on each side of the same base, you can just drop them, and you could use the, simplify that x equals y. All right, here's a few examples on using some of these properties. And you can kind of follow along with the properties because each one sort of goes in the same order. Okay, here we have a log base 4, but we're taking the log of 1. Right? That's always 0. Here's kind of an interesting one. The base that we're using is square root 7. Kind of an interesting base to use. Okay, maybe it could come up in an application problem, but you know, as we're kind of starting with some easier numbers, that's kind of an interesting base. However, what we're taking the log of is the same as the base, which means that's 1. Now, if you compare number 3 to your third property, here it's switched. Okay, now it's like on the outside we have an exponential expression, and then up in the exponent there's a logarithm, but again they have the same base. And you can think of it like the exponent and the logarithm cancel each other out, and that expression would just equal 20. Okay? Again, when we solve, that you're going to see stuff like that come up all the time. Then down here on number 4, okay, both of those are log base 10. But there is just 1 on each side. Which means I can just drop them, and you get a relatively simple equation, but you could solve it without the logarithms, because property number 4 says if you've got 1 on each side and it's the same base, they effectively just cancel each other out. Okay, I want to take you through making a logarithmic graph. If you have the notes out, and you should see there's two slides for it. One is just a graph of a logarithmic function, and the other is a natural log. I'm going to take you through one because the other one's going to be exactly the same. I'll get you started on the second one, but I'm not going to finish it. Now, if I'm not using really the calculator to assist me a lot, which again sometimes we'll have to, sometimes we won't, I'm actually going to start with that. And you might look at that and be thinking, wait a minute, that's wonderful. This is for graphing a logarithmic function, and that's an exponential. Okay? Well, hold on for a minute. I think you'll probably see sooner or later where I'm going with this. Now, the nice part about this one is if you look through your notes from day 1, I think you have it. Okay? Actually, I'm sure you do. We did this graph when we were talking about the basics of exponential functions. We put in -3, and we got an 1/8. We put in -2 and got a 1/4. Now this is the one that we really want to kind of build our way towards, is log base 2 of x. And I've never had much luck showing students how to jump right to log base 2. Which is why I'm starting with 2 to the x. Okay, because this leads us to a concept that we're pretty familiar with. We've seen it time and time again, and we did pretty well with it in Chapter 1, and that's an inverse. Okay? This is now the third time in this lesson I keep coming back to that. Exponential functions and logarithmic functions are, assuming we're talking the same base, they're inverses. Okay? Do you remember what we can do with our first table of values if our second one is the inverse function? We can take them and we can switch them. And I'd have a lot more confidence that you could take that exponential graph and you could make that without any major issues. That just, again, when you're evaluating exponential expressions, they just tend to be easier for us to work with. But that gives you 6 points that you could build the logarithmic graph. Okay? Now, before I put either one on there, I all of a sudden jump over here and I'm like graphing this random line in green. What is that all about? It's a little bit random, not totally. We've talked about how these two functions are inverses, so I am graphing the line y equals x. And we should see a relationship between these two graphs with it. That is our exponential curve. On your homework and on a quiz or a test, it's unlikely that I would ask you to do this. If it helps, you certainly could. The table might, you wouldn't need to graph the exponential one. Again, I'm still sticking with the inverse thing, and I want you to see the reflection over y equals x. But it would be fine, like on a test, if it just asked you to make the logarithmic graph, that's the only one that you actually plot the points for. And there is log base 2. Nice reflection over y equals x. Again, with the whole inverse thing, notice how it does the opposite. Exponential growth models start kind of slow and then they go faster and faster. Logarithmic functions do the opposite. They increase very quickly at first and then they start to slow down. Okay, the exact opposite of an exponential. All right, really what I want here, I just want to get you going on this one. Again, I'm not going to do the whole thing. I just don't think I need to because it's going to end up being so similar. I really just want to talk about natural logs. It's kind of leading us into the second day. Anytime you see a natural log, you need to think base e, right? And we saw the other day, that's like 2.71, 2.72, okay? We kind of derived e in class, in section 1. 1 plus 1 over x to the x power when we put in x values that were really big. All right, so if you wanted to here, and this one you'll need a little bit more calculator assistance, but you have an e button that we've seen on the calculator. Okay? Start with e to the x. And then notation-wise, what you'll see is if you see ln, right, that's going to be a natural log. And anytime you see a natural log, that's talking about base e. And again, in the second day, we'll talk more about those. But if you wanted to make a graph of each one of these, again, the only difference for evaluating like e to the x, because you're going to get some decimals, you would need to use a calculator that has a base e button. And for your y values, expect long decimals that you're going to round to 1 or 2 decimal places.